CDs use a sample rate of 44.1 kHz. Modern high-resolution audio at 96 kHz and 24 bits. We're looking here at a 100 Hz sine wave in SoundForge. This one right up at 10 kHz. As our sample rate is 48 kHz, in fact these dots will be connected with a smooth curve. And not just any smooth curve. Here's a 20 kHz sine wave. As 20 kHz is less than half the CD standard sample rate of 44.1 kHz, CD resolution audio is quite capable of recreating a 20 kHz sine wave. Let's say to 96 kHz. Now I can represent frequencies right up to 48 kHz. But this 20 kHz sine wave isn't reproduced with any greater accuracy. 20 kHz is usually considered to be the upper limit of human hearing. I'm not ashamed to admit that I can't hear this 20 kHz tone at all. So if a CD standard sample rate of 44.1 kHz, most consumer speaker systems can't reproduce frequencies higher than 20 kHz. Here's a 7 kHz sine wave. Now here's another sine wave at 25 kHz. I've set my system sample rate to 96 kHz. We get a 7 kHz sine wave that we can hear, plus a 25 kHz sine wave that we can't hear. Adding this to the 7 kHz sine wave, we see a third harmonic appear at 21 kHz. Now let's add in the 25 kHz sine wave as well. These are well below 20 kHz. Brick wall filtered to remove everything below 24 kHz. If you band limit the signal by removing the inaudible content above 20 kHz, you might actually end up with a cleaner, better quality result. In this spectral display, it shows as a diagonal line starting at 20 Hz and sweeping up to 20 kHz. When it reaches the Nyquist limit at half the sample rate, in this case 24 kHz. Okay, now let's try the same thing, but with our sample rate set to 96 kHz instead of 48 kHz, where the resulting aliasing is above 20 kHz and can be considered inaudible. When the original sweep reaches 20 kHz, the aliased third harmonic is still up at 36 kHz. If we try this at 96 kHz, it's certainly better. We could go to 192 kHz. Again, it's a lot better. But while many of you will have interfaces capable of running at 192 kHz, so let's revert to a 48 kHz sample rate. Everything above 24 kHz then gets filtered out before the sample rate is dropped back down to the original rate of 48 kHz. Let's try doubling the sample rate to 96 kHz. If I switch back to a 48 kHz sample rate, so in this case, perhaps it's better to run the project at 96 kHz. I'm running the project sample rate at 96 kHz. Let's have this somewhere around 4 kHz. But the 4 kHz components of the original guitar DI signal are not very high in level. So the aliased components below 20 kHz are likely to be very low in level and probably not significant. So running at 96 kHz instead of 44.1 or 48 is probably enough to prevent aliasing being a problem. If we go up to 192 kHz, the aliasing is much improved for the first saturation stage. Now let's try dropping the sample rate back to 48 kHz. Now each instance of Saturn upsamples the input signal 8 times, applies its processing with an internal sample rate of 384 kHz, then filters out the harmonics higher than 20 kHz when downsampling. Let's start with the project sample rate at 44.1 kHz. Now let's switch the sample rate to 96 kHz. But the synths are now generating 96 kHz audio. Now let's switch back to 44.1 kHz. Let's quickly look at the difference between 44.1 kHz and 48 kHz. So you might as well run at 44.1 kHz for music productions. At 44.1 kHz, these have to be extremely steep in order to remove everything above 22.05 kHz without affecting a signal at 20 kHz. If I switch to a 48 kHz sample rate, however, these filters can be somewhat less severe, as they now only have to remove content above 24 kHz. In this respect, you could say that 48 kHz is twice as good as 44.1 kHz. This might be why many pros choose to track and mix at 48 kHz instead of 44.1. So here's my little test mix running at 44.1 kHz again, and now here it is rendered at 48 kHz, then converted offline afterwards. However, aliasing is actually likely to be inaudible in most cases.